Welcome to the third lecture on this course on 3G and 4G wireless communications, that is third generation and fourth generation wireless communication systems. In the previous lecture, we have developed a robust analytical model to characterize our wireless communication system, and we specifically modeled the wireless communication channel as a sum of a large number of multi-path components, and more specifically for a narrow band signal we said the system model can be expressed as Yb of t, where Yb of t is the received signal, equals Sb of t, where Sb of t is the transmitted baseband signal, times a complex factor. This complex factor is summation a I e power minus j 2 pi f c tau I. There are L components in this summation corresponding to the L multipath components, attenuation factors a I and delays tau I. This is a complex factor or a complex coefficient, and we said the received signal is the input signal times this complex coefficient. We said this complex coefficient has a name. This complex coefficient can also be known as complex fading coefficient, fading because the magnitude of this is a random quantity which varies from time to time, place to place, and this in turn causes the signal power to fade. So, this is known as a complex fading coefficient. The wireless system model can be expressed as Ybt equals h times Sb of t, where h is the complex fading coefficient, and this is very different from the wireline channel model or wireline system model, where Yb of t is simply Sb of t, since there is no constructive or destructive interference due to the multipath components. There is only one component, and hence Yb of t is simply Sb of t, that is the received signal is simply the transmitted signal in a wireline communication system. And we also said that the complex fading coefficient can be expressed as x plus j I, where x is the real part and j is the imaginary part, and each x of the x and y are the sums of a large number of random components. So, each of them can be assumed to be Gaussian in nature. We specifically assumed them to be x to be a Gaussian variable of mean 0 variance half, y to be a Gaussian variable of mean 0 variance half, and x and y are independent in nature. The joint distribution of x and y can be derived as f x y equals 1 over pi e power minus x square plus y square, and we also derived the joint distribution of the channel fading coefficient a in terms of a the magnitude and phi the phase, and it is given as 1 over pi e power minus a square times a, that is a over pi e power minus a square. So, the joint distribution in terms of the variables a and phi is given as a over pi e power minus a square. Alright. Now, let me derive the marginal distributions. As we said before we began this discussion, we are interested in the statistical properties of the gain of the wireless channel. That is, we want to look at how the gain, which is how the factor a behaves in a wireless communication system. So, I will derive what is known as the marginal distribution, that is from the joint distribution of a and phi, that is the amplitude and phase. I will isolate the distribution of the amplitude a, and that is simply arrived at by f of a of a, which is the marginal distribution with respect to a, the marginal with respect to a is simply integral, that is I integrate over phi, and phi is a phase. So, it varies from minus pi to pi, that is simply minus pi to pi of f of a comma phi of a comma phi of d phi, and this is simply minus pi over pi a over pi e power minus a square d phi. As you can see, there is no term in this integrand here that depends on phi, hence this comes out of the integral, and this can simply be written as a over pi e power minus a square integral minus pi to pi of d phi, which is simply integral minus pi to pi of d phi is 2 pi. So, this is 2 pi a over pi e power minus a square, which is simply 2a e power minus a square. All right. So, the marginal distribution of A, the amplitude of the fading wireless channel, also known as the envelope of the wireless channel, because look at this, A is nothing but square root of x square plus y square, that is square root of where x is the real part, y is the imaginary part, hence A is also known as the envelope of the fading channel, envelope of the fading channel, and we have seen that f a of A is simply 2 a times e power minus a square. This is a very important result for us. This distribution has a name. This distribution is known as the Rayleigh distribution. I am writing this out prominently because this has key place in all wireless communications theory. This is the standard channel model that is used in a wireless communication system, and this is known as the Rayleigh fading distribution. This is the Rayleigh distribution, and a fading coefficient which has this distribution is the Rayleigh fading distribution or the Rayleigh density function. Right. And this obviously, since the amplitude is positive, this is between 0 less than a less than equal to infinity. Right. This is the Rayleigh distribution. Let me show you how a plot of the Rayleigh distribution looks like. What you can see in this PDF here is the Rayleigh distribution, that is 2a e power minus a square, that is plotted. What it shows is the probability density of the Rayleigh random variable, or the probability density of A, which is the magnitude of the fading coefficient, given any interval. For instance, let us consider the interval 0.5 to 1 over here. The probability that the magnitude lies in this interval is simply the integral of the density function in this interval, which means if you look at this, there is very low probability that the coefficient takes very high values, also low probability that it takes very low values close to 0, and with very high probability it rises in a range somewhere in between. Now, what is important for us is this range of the fading coefficient here, which is close to 0, because when the magnitude of the fading coefficient is close to 0, it means that the fading coefficient has very low gain, which in turn means that the signal power received is attenuated, it's significantly attenuated. So, the signal power received is extremely low, all right, and such a scenario is known typically as a deep fade. Let me write this here. This is known as a deep fade scenario when the channel magnitude of the channel coefficient is very low. Let me go back to the notes. So, we said that the Rayleigh fading coefficient has a density that looks something like this. Let me draw this approximately over here. This is f of A equals to a e power minus a square, and we said that when a is very close to 0, the received power is very low, and this is the region corresponding to the channel, the wireless channel being in a deep fade. The technical term used for this is a deep fade, because the received signal power is almost 0. Alright, and this can be have adverse effects on the wireless communication system, because if the received signal power is 0, then essentially there is no signal that is received, or in a sense the received signal cannot be distinguished from the noise. Alright, so this is a problem in the wireless communication system. Alright, so this is the Rayleigh fading distribution. We will talk more about this deep fade scenario later, but also let me derive, to complete our discussion, let me derive the marginal distribution of the phase phi, that is I want to derive the marginal distribution of the phase phi of the fading coefficient, and this is given as f phi of phi. Now, I have to integrate over a, that is I have to integrate a over pi e power minus a square over a, over the limits of a, that is 0 to infinity, integral a over pi e power minus a square, and this can be written as 0 to infinity 1 over 2 pi into 2a e power minus a square dA. Integral 2a e power minus a square is simply e power minus a minus e power minus a square between 0 and infinity times 1 over 2 pi, integral minus e power minus a square between 0 and infinity is simply 1. So, this is essentially 1 over 2 pi. So, the marginal with respect to phi, that is the marginal distribution of phi, is 1 over 2 pi. As you can see, this does not depend on phi. 1 over 2 pi is a constant which does not depend on phi. Hence, this is essentially uniformly distributed between the interval minus pi to pi. This corresponds to uniform distribution in the interval minus pi to pi, that is with equal probability it can take any value in the interval minus pi to pi. And now, let me come to another major point about this joint distribution, which is f of a comma phi, which is a comma phi can be written as a over pi e power minus a square. I can also write this as 1 over 2 pi times 2a e power minus a square. And now, you can observe something interesting, which is this is the marginal with respect to phi, 1 over 2 pi is the marginal with respect to phi, 2a e power minus a square is the marginal with respect to the amplitude. The joint distribution of with respect to a phi is the product of the two marginal distributions. Hence, a and phi are independent random variables. So, let me mention that here a and phi are independent This is a very important result, because it says it characterizes the fundamental nature of the fading coefficient. It says that the amplitude A and the phase phi of the complex fading coefficient are essentially independent, which means the fading coefficient is magnitude is distributed Rayleigh, that is 2a e power minus a square, and the phase is distributed uniformly between minus pi and pi, and both these random quantities are independent of each other. Alright. So, that is the important concept that we learned here, and this completes our statistical characterization of the probability density functions of the magnitude as well as the phase of the complex fading coefficient. Let me just refresh your knowledge regarding this. We said Yb of t in a wireless channel can be written as h times Sb of t, where Sb of t is the transmitted baseband signal. Now, this h is a complex fading coefficient, h is a complex fading coefficient which can be expressed as a magnitude times a complex phase factor e power j phi. Distribution of A or the density of A is essentially 2A e power minus a square, which is the Rayleigh density in the interval 0 less than equal to a less than infinity, and the density of the probability density of the phase factor phi is uniformly distributed 1 over 2 pi in minus pi less than or equal to phi less than or equal to pi. This characterizes the magnitude and phase components of the Rayleigh distributed wireless channel. Let me now take a brief example to illustrate to you the significance of the analysis that we carried out. All right. So, let me give you an example that will illustrate to you the use of the wireless channel, of the analysis of use of characterization of the statistical properties of the wireless channel coefficient that we just carried out. So, as we said, the magnitude A corresponds to the attenuation of the signal while propagating over the wireless channel. Now, what I want to find out, let me frame my problem. My problem is as follows. I want to compute the probability. So, what is the probability? What is the probability that a transmitted signal is attenuated by more than 20 dB. So, I am transmitting a signal from the base station, I am receiving it at the mobile station. I want to find out the probability. Remember, the gain of the signal at the receiver is a random quantity depending on the multipath propagation environment. I want to find out what is the probability that this attenuation is worse than 20 dB. I mean, which means, so what is the probability that the attenuation, that the overall power attenuation is worse than 20 dB. Let us consider this signal simple example. Now, power versus this is power in dB. So, power in dB, I want to find out what is the probability that this attenuation is worse than T dB. So, remember, this is the power gain is this is an attenuation. So, this is negative. So, I want to find out what is the probability if G is the gain of the channel. We know that the attenuation is 10 log to the base 10 of G, because G, remember, is the gain in power, G equals a square. I want to find out what is the probability that 10 log 10 G is less than or equal to minus 20, all right, which means I want to find the probability that log of G to the base 10 is less than or equal to minus 2, which means I want to find out the probability that G is less than or equal to 10 power minus 2, which is equal to 0.01. All right, I want to find out the probability that G is less than or equal to 0.01, so that the attenuation is worse than 20 dB. Now, G equals A square, which means if G is less than 0.01, A square is less than or equal to 0.01, which implies A is less than or equal to 0.1. Now, we know the marginal distribution of A or the probability density of A. So, I can simply compute this probability, that is A less than or equal to 0.1, as integral 0 to 0.1 to A e power minus A square dA, where 2A e power minus A square is a probability density function of A, and this is simply integral 2A e power minus A square is minus e power minus A square between the limits 0 and 0.1, and this is simply the integral of 2A e power minus A square between 0 and 0.1, and this is simply minus e power minus A square between the limits 0 and 0.1, and that is simply 1 minus e power minus 0.01, which is 0.01. So, the probability, so let me summarize what we have computed. The probability that the attenuation is worse than minus 20 dB is 0.01 or essentially 1%. All right. So, knowing the statistical behavior of the complex fading coefficient, one can predict the probability with which the received signal is attenuated greater than minus 20 dB. For that matter, the probability that the received signal is attenuated below any set threshold. All right. Similarly, I can also compute, to illustrate another example. Let us talk about another example. What is the probability, for instance, what is the probability that the phase phi lies between minus pi by 3 to pi by 3. I want to compute the probability that the phase of the complex fading coefficient lies between minus pi by 3 to pi by 3. As we have seen earlier, the phase follows a uniform distribution 1 over 2 pi between minus pi to pi. So, the probability that the phase lies between minus pi by 3 to pi by 3 is simply the probability that minus pi over 3 less than equal to phi less than equal to pi by 3 is simply the marginal, that is 1 over 2 pi d phi integrated between the limits minus pi by 3 to pi by 3, and this is simply 1 over 2 pi over 3 minus pi over 3. This is simply 1 over 2 pi times 2 pi over 3 equals 1 over 3. So, the probability that the phase lies between minus pi by 3 and pi by 3 is essentially 1 over 3. The probability that minus pi by 3 is less than equal to phase less than pi by 3 is 1 over 3. Thus, knowing the statistical properties or having characterized the statistical properties or the statistical behavior of this complex fading coefficient, we are in a better position to understand a lot of aspects about the behavior of this wireless communication system, especially in terms of the magnitude, which essentially describes or which essentially determines the attenuation of the received signal, and also the phase, which essentially describes the phase offset of the received signal. Alright. So, this completes one of the sections where we characterize the statistical behavior of the complex feeding coefficient. Now, we want to better understand the difference between a wireline communication system and a wireless communication system. What we intend to do now is essentially look at our newly developed model for a wireless communication system, use that to characterize the performance of the wireless communication system and compare that with the performance of a traditional or a conventional wireline communication system. All right, and the theory that we have developed so far, which is essentially building up a model for the wireless communication system and the analyzing the statistical properties of the complex feeding coefficient, will aid us in this endeavor. So, now let me start with the next section, which is performance of wireless and wireline communication system. So, let me start with the next topic, which is the performance of wireless and wireline communication systems. And when we say performance of a communication systems, what we mean most often is bit error rate performance of wireless communication system. So, this is bit error rate, or what is also abbreviated as BER, performance of the BER performance of the communication system. All right. What we most often mean is the bit error rate, because remember, every communication system transmits, digital communication system transmits information in terms of binary information symbols, that is ones and zeros. So, every communication system transmits a string of ones and zeros. These are coded and transmitted over the information channel. Now, when you decode this transmitted stream, there are errors in the decoded or the detected information stream. For instance, I can detect this transmitted stream of 100,111,0100 as 100. Now, instead of the 1, there is an error here in this detection 110. Again, there is another error, that is this 1 detected as a 0 and 00. So, this transmitted stream of 100,111,0100 has been detected with some bit errors, as this one of the ones has been flipped to a 0 and one of the ones here has been flipped to a 0. So, these are the bit errors. These are the bit errors, and the rate at which these bit errors occur, or the probability at which there are bit errors in the information stream, is known as the bit error rate. So, bit error rate is simply probability of bit error in information stream. So, the bit error rate is simply the probability of bit error in the information stream. For instance, let me give you an example. If I transmit 10,000 bits and 100 of them are received in error, I have transmitted 10,000 bits, 100 of them are received in error, then the bit error rate is simply 100 divided by 10,000 1000, which is essentially 10 power minus 2 or 0.01. So, the bit error rate is 0.0. Alright, this is a simple example just to show you what we mean by bit error rate. Bit error rate is simply the probability, the rate at which the bits are received in error, and that arises due to two effects. The predominant effect that you must be familiar so far is because of the noise at the receiver. There is another effect that arises in a wireless communication system, and we are going to see that, or we are going to characterize that shortly. Alright. So, we want to analyze the performance of wireless and wireline communication systems and essentially compare the performance of these two systems, so that we understand what is the difference of wireless communication systems compared to the conventional wireline communication systems. For that, let me take the following approach. Let me first start with the analysis of the bit error rate of a wireline communication system. Since these are conventional systems, I want to first introduce you to the bit error rate performance of these systems, and then derive the performance of a wireless system and compare these two, so that we understand the difference. So, let us start with a bit error rate performance BER of a wire line communication system. I want to start with the bit error rate of a wireline communication system. Now, as we said before, we introduced a model for the wireline communication system. Before we said y equals x, that is the coefficient essentially is 1, because there is no multipath propagation, hence there is no multipath interference, which means the received signal is what is transmitted, except there is going to be some noise at the receiver. So, this can be represented as y equals x plus n. I will write this down clearly over here, which is y equals x plus n. This is also termed the system model of a communication system. This equation here is specifically the system model of a wireline communication system. This n is assumed to be Gaussian noise, and more specifically white Gaussian noise is simply noise whose power spectral density looks uniform over all spectral components. I again urge you to revise your knowledge about white Gaussian noise by going back to lectures on communication engineering on NPTEL. N is white Gaussian noise, and more specifically let me characterize n as having a Gaussian distribution of mean 0 and variance sigma n squared, that is sigma n squared is the variance or the power of this noise. This noise here, look at this, this is an additive noise, this plus symbol, this is an additive noise, alright. Hence, I have my signal x, my noise is adding onto this transmitted signal x, and this noise is white Gaussian noise. Hence, this channel also has another name. It is known as AWGN channel, which stands for additive. A stands for additive, W stands for white, G stands for Gaussian, and N stands for noise. So, AWGN stands for additive white Gaussian noise. So, the traditional digital communication channel is essentially an additive white Gaussian noise channel, or essentially this is also another name. AWGN channel is another name for the conventional wireline communication system. We will start with analyzing the bit error rate performance of this channel. In this AWGN channel, let me consider the information symbol 1 which is coded as the level +1 and the information symbol 0 which is coded as the level -1, that is 1 which is coded as +1 and the binary information 0 or the bit 0 which is coded as -1, and I am transmitting them with a certain power from the base station. So, these will be scaled by square root of p, where p is the transmit power. Alright. So, what am I transmitting? For 1 I am transmitting plus root p, square root of p, a voltage of plus square root of p, and for a 0 I am transmitting a voltage of minus square root of p. Depending on the level I receive at the receiver, I know if a 1 has been received or a 0 has been received. Alright. I look at my received level. If it is greater than 0, I conclude that it is a 1. If it is less than 0, I conclude that it is 0. This you must be familiar from your basic introduction to digital communication systems. I am assuming the users have a basic undergraduate knowledge related to digital communication systems and bit error rate. This in fact corresponds to BPSK, which is binary phase shift keying system, which is a binary phase shift keyed system, which is, look at this, I am transmitting a phase of plus or a phase of minus. So, this is two phases or a binary phase. So, this is a digital communication system which employs a BPSK constellation or a binary phase shift keyed system. If the received level is greater than 0, I conclude that an information symbol 1 has been transmitted. If the received level is less than 0, then I conclude that an information symbol 0 has been transmitted. So, now to derive the probability of bit error, the probability of bit error is simply the probability that if a 1 has been transmitted or if plus root p has been transmitted, what is the probability that the received level is less than 0? This is because there is noise at the receiver, and similarly if a 0 has been transmitted, that is if a minus square root of p has been transmitted, what is the probability that the level is greater than 0? This happens because again there is noise at the receiver. Alright. So, let me consider the case where a 0 has been transmitted, because the other case is symmetric. So, let me consider a case, where the bit 0 is transmitted. Consider the case where the bit 0 is transmitted. Now, 0 corresponds to minus root p. So, my received signal is y equals minus root p plus noise. Right? What I am saying? I am saying is the bit 0 has been transmitted. We saw in the previous page that 0 is coded as minus square root of p. So, I am transmitting minus square root of p. What I am receiving is minus square root of p plus n, where n is the noise at the receiver. Alright. Now, there is a bit error. A bit error occurs if the level received is greater than 0, because then it will be decoded as a 1. So, a bit error occurs if y is greater than 0, corresponding to a transmission of minus square root of p, which means n minus square root of p is greater than 0, which means n is greater than square root of p. What I am saying here is, in this situation a bit error rate occurs if n is greater than square root of p, because it will be decoded as corresponding to 1, and the other case with respect to 1 is symmetric in the sense that a bit error will occur if n is less than minus square root of p. Right. So, these are symmetric, and that is why I am analyzing only one of the scenarios. All right. Now, n, let me recall for you, is distributed as normal with variance power sigma n square, that is n is additive white Gaussian noise, it is mean 0 sigma n square, variance sigma n square. So, now I want to find out the bit error rate, which is simply the probability, as we saw in the previous slide, that n, or the previous page, that n is greater than root p. This is simply the probability density function of n integrated between the limits square root of p and infinity. So, this is simply, let me write it down clearly, the probability density of function of n integrated between square root of p and infinity, and this probability density function is Gaussian, which we have seen many times so far, is simply 1 over square root 2 pi sigma n square e power minus x square over 2 sigma n square dx, right. X is the integration variable. I am saying the probability that n is greater than square root of p is simply integral square root of p to infinity 1 over square root of 2 pi sigma n square e power minus x square by 2 sigma n square. Now, let me do a simple manipulation, let me do a substitution of variables, let me denote x by sigma n equals t, which means dx equals sigma n dt. So, this integral can be written as integral, the limit become, since t is x over sigma n, the limit becomes square root of p over sigma n, that is square root of p over sigma n square, that is square root of p over sigma n square to infinity over sigma n, which is infinity 1 over 2 pi sigma n square e power minus x by sigma n is t. So, x square by sigma n square is t square. So, this is simply e power minus t squared by 2 dx is sigma n dt, and the sigma n on the right and the sigma n in the square root in the denominator cancel, and then the net expression that we derive is the probability that n greater than root of p, which is in fact the probability of bit error is simply integral p over sigma n square square root of p over sigma n square to infinity 1 over square root of 2 pi e power minus t square over 2 dt, and this is also the probability of bit error. This is essentially the probability Now, this function on the right, look at this function on the right, this function is in fact nothing but the cumulative density function of the standard normal variable. Look at this, the standard normal variable has a distribution as we saw before given as 1 over square root of 2 pi e power minus t square over 2. Now, let me define the standard q function as q of v equals integral v to infinity 1 over square root of 2 pi e power minus t square by 2 dt. What q of v denotes is essentially the probability that the standard normal is greater than v and lies in the interval v and infinity. Alright, this is a q function, this is known as the q function, and this there is no closed form expression for this. This has to be computed manually and there are tables to compute the q function. So, now this as you can see, this as you can see is simply q of square root of p over sigma n square. Alright. So, the bit error rate of this digital communication channel of the wire line channel, wire line communication system is simply q of square root of p over sigma n square. And remember, let me go back to our system model y equals x plus n. Remember, p is nothing but signal power, p equals the signal power, and sigma n square is nothing but the noise power. Hence, I can also write this bit error rate as bit error rate equals q times square root of p over sigma n square, but p over sigma n square as we see is the ratio of signal power to noise power, or the signal to noise ratio, which is abbreviated as SNR. All right. So, this is q of square root of SNR. All right. So, this is q of square root of SNR, that is the bit error rate of a conventional wire line communication system. All right, this is the bit error rate of a wireline communication system. In other words, given a certain signal to noise ratio, this denotes the probability that a bit is received in error. All right. For instance, it say if you say you transmit about 10,000 bits, the number of bits or the average, or an average the number of bits received in error is simply the bit error rate times 10,000. All right. So, that is a rough analogy that you can use to understand, and obviously it makes intuitive sense because this q function is a decreasing function of SNR, because look at this, the q function is the cumulative distribution function of the Gaussian, which is for any point x. This represents the area under curve to the right of x. As x is decreasing, this area x is increasing, this area is decreasing, which means as SNR is increasing, the area is decreasing, or which means the probability of error is decreasing, and that makes intuitive sense because as SNR is increasing, signal power is increasing with respect to the noise power. So, you expect your reception to be better, or in other words the bit errors to decrease. All right. So, this all of this makes intuitive sense, that is, this is q of square root of SNR, and as the SNR is increasing, the bit error rate decreases. In the ideal case, if the signal to noise ratio is infinity, that is either signal power is infinity or noise power is very small, that is 0, then this is q of infinity, which you can see is the integral to the right of infinity, which is essentially 0. So, which is essentially 0. So, as SNR tends to infinity, this probability of bit error tends to 0, which makes intuitive sense, and this is the bit error rate performance of a wire line communication system. Let me do a brief example to illustrate to you how to compute the bit error rate of a wireline communication system. Example, at an SNR of 10 dB, so this is the problem, at SNR dB equals 10 dB, what is the probability of bit error, or what is the bit error rate of the wireline communication system? Is the BER of wireline communication system. And the solution is as follows. Remember, SNR in dB is 10 power log 10 of the SNR or the linear SNR. Hence, 10 times log 10 of SNR equals 10 dB, which means log 10 of SNR equals 10 dB over 10, which is 1, which means SNR equals 10 power 1, which is 10. The SNR is 10, and the bit error rate corresponding to this is obviously Q times square root of SNR, or bit error rate is Q times square root of 10. As I said, again, there is no closed form expression to compute the Q function. This has to be computed from the tables. I have pre-computed this value Q square root of 10, and this is given as 7.82 into 10 power minus 4. All right. This is the bit error rate, and as for our per our analogy below, if we transmit 10,000 bits, then number of bits in error. So, the number of bits in error in 10,000 bits equals 7.82 into 10 power minus 4, which is into 10,000, which is essentially 7.82. So, what it roughly means is that out of 10,000 bits, 7.82 or close to 8 bits are in error. Now, remember, this is a random quantity, so it varies again from block to block. So, in one block of 10,000 bits, you might find 5 errors, in another block you might find 10 errors, in some block you might find 8 errors, and so on. On an average, when you look at the average number of bits in error, that is essentially around 7.82 approximately in the long term. That is what this statistic here means. All right. So, the bit error rate is 7.82 at an SNR of, remember, 10 dB. So, bit error rate is 7.82 in 10 power 4, 10 power minus 4 at SNR dB equals 10 dB. All right. And let me just, before I conclude this lecture, let me just show you how the plot of the bit error rate looks like. For instance, this is the plot of the bit error rate, or this is essentially the Q function of square root of SNR with Q function of square root of SNR, and on the y axis is the probability of bit error. So, what this says here is, for instance, I can read this as follows. For bit error rate of 10 power minus 4, as we have the SNR required is essentially something around between 11 and 12 dB, probably around 11.2 dB or something like that. For a bit error rate for at SNR equals 10 dB, which is what we just computed, the bit error rate corresponding to this is somewhere around here, and this we have computed as being 7.84 into 10 power minus 4. All right. So, we computed the bit error rate at SNR 10 dB. This point corresponds to the 10 dB point, and it says the bit error rate is 7.84 or this is 7.82 into 10 power minus 4. So, the bit error rate corresponding to 10 dB is 7.82 into 10 to the power of minus 4. That is the probability that one of the received bits is in error. All right. So, with this analysis of the bit error rate of a wireline communication system, I would like to conclude this lecture regarding the performance analysis of wireline communication system. Remember, we have done this in order so that we can also derive the performance of a wireless communication system similarly and compare both these systems so that we get an idea of what is the difference between the wireline communication system on the one hand and a wireless communication system on the other hand, so that we have a better understanding of the properties and the differences between these two systems. Thank you.